I'm Frank Bergmann from living in Barcelona, having this talk and the paper together with Fenton from Ireland. Brian is a mathematician. He knows about magic. And I'm an engineer and actually a business guy, and I like things that work. That's, I think, definition of engineer. And together we've come up with some insane ideas that we want to present here. And hope it's going to be at least entertaining. So we propose a new, or partly started to implement a new cognitive architecture, which we called scene-based reasoning. And this cognitive architecture is, as some reviewers said, is basically just common sense. I would basically agree with that. So nothing really new if you look at this little diagram there. The paper we've written goes very much in detail what we propose and details on how we want to do things. In this talk, I want to more talk about what we want to achieve, and this is not included in the paper. So the motivation for this cognitive architecture comes from psychology, philosophy. There's a philosopher called Thomas Metzinger, a German guy, but basically teaching in the US a lot. And he's got this self-model theory of subjectivity. So it's the C word. Everybody knows about the C word, consciousness. We're not going to mention it. So this is the C word, and it's also related to the Q word, which is qualia. We're also not going to mention this, and not going to talk about it. So he explains, he's got a theory on how C word and Q word might work, and his theory really rests on this concept of self-model. He talks about a phenomenal self-model of subjectivity. As an engineer, this is all too fuzzy to me. I'm a lowly engineer, so I want to break this down into the actual levels and as a systems architecture. So what we're trying to achieve in this cognitive architecture is providing partial implementations or reasonable building blocks for an implementation of these 10, 11, 12 levels of self-models that I'll show in a second. I'll be very quick here in this talk and focus more on the actual architecture. On Saturday afternoon or morning, there's a workshop on self-model, self-referentiality and cognitive architectures. So that will be 45 minutes, a little bit more going deeper into Metzinger's theory and a little bit deeper into self-model. So I'm trying to be very brief here and to get along with my 18 minutes. There is an implementation, a very first implementation of Towers of Hanoi working. There's this tiny cog source. We didn't find a better name yet. There's this site on SourceForge where we have a kind of a version of the paper as a wiki format, and there is some code that actually works, but I wouldn't call it precisely intelligent yet. Self-models. We are the self-model guys. That's what is a self-model? Metzinger's got his philosophical self-model. I don't want to talk about that here. What's important is the human mind has models about itself on several layers. And Metzinger doesn't explicitly enumerate these layers, so this is our work, our humble work, and it's related to the architecture, like with a planner and a description logics, reasoning stuff that we actually want to use for implementation. So with a specific, with another cognitive architecture, these layers might look different. It really doesn't matter. So they're adaptive. So we got some physical layers. The first one is like the Google car layer. There's a physical space, and the car itself is one of these physical bodies. Or I get my limbs, and this is my body model. There's planning layer. There's some temporal planning activities going on. And having a model, a self-model of planning means, for example, that for the plans that I develop, here in the planning part, oops, this is like a plan, have dinner, get food, that I do have a model, a meta model of this plan. I'm just taking this one example at the moment. And that I not only can say, for example, the probability of success on this plan, but what we propose here as a very specific element is that we have a meta representation of these task decompositions. That's planner subtasks, like in a 2D diagram style. So this looks like a plan, like you're looking at a plan, but imagine that the system itself is able to deal with two-dimensional, three-dimensional scenes, like looking at objects, like visual stuff, and it is an introspection subsystem is capable of mapping its internal plan representation, which is like Java or Prolog structures with pointers and stuff, into like a 2D diagram style, or 3D, really doesn't matter. So I want you to look at this not as a human representation of what's in the machine, but this is the representation the machine will look at. And now I'll explain the mechanisms that of like working on visual data, on 3D data, that the engine that actually works on these is able to work on these meta representations, and using this general engine on meta representations, we'll be able to handle most of these self models in a engineering or software architect perspective, more or less realistic way. We propose a number of subsystems that are quite far out. For example, we say we need plan recognition as the key element for learning and curiosity and understanding what's going on there. Plan recognition is not very well understood yet, and there may be practical issues implementing it. So we're proposing pretty high-level building blocks, so that's true, and not all of them are yet readily available. But all of them are feasible, reasonable, so nothing esoteric or beyond super cognitive here. So, yeah. So I'm now, how many minutes? 10 minutes. I'm going to show the three main components of this architecture now, which is scenes, which is basically the representation level, reasoning, and a planner level for temporal stuff. So this is a little bit more detailed. So I'll dive in a few more details right now. And yeah, if there's, I'll dive into details. So the lowest level of this core of scene-based reasoning is the scene. That's giving the name for the thing. So a scene, we define this scene basically as a 3D scene graph, as in computer gaming. So forget everything about cognitive architecture, systems, whatever you know. So let's think about computer gaming, like Unity 3D, the OpenCog guys are using and stuff. So scene graph is like this guy here. It's a 3D body representations of the visual camera input sensor data, okay? So now there's, based on this grounding level, we'll have several abstraction layers, but we still call everything a scene, yeah? So from these physical objects, we might abstract to like the object Frank, which consists of like limbs and a body and a talking head or whatever. So this is, yeah, scene level. That's the semantic level. So once we abstract from the scene, 3D scene, we get at a semantic network level, where we're using description logics here as a knowledge assembler, low-level first mind type, simple inferences. So we represent the scene data in one or two levels higher as a semantic network. But this semantic network is used by the planner as a situation. So This is just one world state, and we'll be able to have like dynamics on this world state and model them explicitly with plans and timelines. So, so this world state is dynamic, and then there's an intermediary level here, which is not really well defined here, which we might talk about later. It's a 2D graph level where, for example, a plan, like a diagram, is represented. 2D is a subset of 3D, but we'll have like some special types of inferences on this 2D level, which allows us particularly to work efficiently on the representation of internal data structures, like plan reasoning. Plan reasoning, plugging one plan to the next plan, like just a combination of two sub-plans, is one example of these, of operations on this 2D level. Okay, this is the representation. So we got one scene concept, and it is a generalization of a semantic network towards the lower levels of 3D and towards the higher levels in the temporal spatial dynamics. So the next reason is of this core engine. We're talking about a core engine that will have to deal with like 3D scenes and like internal representations. So just the second level is a reasoning. We use a description logic as knowledge assembler. Two slides further in the future, I'll explain the second mind, how that, about the two minds theory. So we're basically using this description logic as a low-level stuff, more representation than actually reasoning, because the computational properties are not very pleasant and it's not very expressive, and you get into deep trouble if you try to rely on DL. That's my personal experience in a failed PhD 15 years ago. So the third level is a planner. As mentioned before, the planner takes the scenes, that means world states, as situations, that are connected by actions. So I'll skip the details a little bit. We're going to stress this task decomposition stuff, hierarchical task networks. It really reduces the search space, the state space. So it's nearly something. It's a continuum between planning and procedural execution with like logic programming, prologue type stuff in the middle. So with this HTNs, you can go all the way, like just execute something that you thought about before, like brushing your teeth, and like completely free planning. There is a goal I want to achieve, a goal state, an end state, and look at the actions that might get me there. So it's a very interesting, relatively new development in the planner community, and I really recommend looking at that. Okay, this is the overall architecture again. There's the few usual suspect subsystems around, like, for us, plan recognition is important because it will like observe other objects, other agents doing things. This one-shot learning thing, I think we can do it with plan recognition. We just recognize the plan that this person was executing, or hopefully. What is important is this little loop here. And we got this attention subsystem and the persistent goal hierarchy here, just in any robotic, whatever control system, together with this execution part from the planner. We get a deduction system again. So this is the second mind. So we assume that there is the difference between the fast neural networks in our brains and then the reflection part, where we can take patterns, meta-representations from all of these other areas into the reasoning process. So this is, the loop. So this is the engine. These three elements represent the engine, or one engine, for like providing the necessary mechanics on working on the self-models. So maybe we'll look a little bit more on these self-models here. Getting towards the end, I got 3 more minutes. Looking into these even more in detail and on Saturday. Hope to see some of you guys there. And it's only 45 minutes talk and then 45 minutes discussion. So it's very, I hope that there is some discussion going on. Maybe if you have questions or contributions, I would be very, very happy to provide you with the time there to discuss with you guys. So there's yeah, these self models here. Planning is easy. This is just plan statistics. Intention is the next step in a plan. Goals is the end state, the desired outcome of a plan. There's a goal hierarchy. I want to be rich, I want to be famous, and I need to get a better job in order to, and I need to get financing for this project anyway. These are the goals. Social model, we'll leave this to Saturday. We get some very specific ideas how BDI, these belief, desire, intention architectures, could work with self-models and other models. There's a historical model, there's the belief model, basically consisting of this first mind, description logics hierarchy, and we, on Saturday, we'll dare to talk about a flow of mental events. Please remove thoughts here, this is a no word. Flow of mental events, self-model that will model like, if you reach the reward function of a goal, this is a mental event. Wow, got it. Or if you get an idea on how to get to a goal, you manage to complete a plan, like to create a plan to get somewhere. Hey, got a plan, I got an idea. Sensations, whatever. These are mental events, and providing like a rolling short-term memory on them, the system will be able to talk about its own mental events. Not in an esoteric, not in an abstract way, but a very concrete way, because all of these self-models are very concrete. There is internal data structures representing them, and we can look at the history of them. Thank you very much. That's it. Yeah, please remember the workshop on Saturday. Thanks.